Remember when Dr. Strange looked into 14 million possible futures and found only one where the Avengers could defeat Thanos? What if I told you that quantum computers are doing something just as mind-bending? Unlike our traditional computers, which can only process one possibility at a time, quantum computers can explore countless outcomes simultaneously, just like Dr. Strange did. And this incredible ability is what makes quantum computing one of the most revolutionary technologies of our time. To understand how quantum computers are revolutionizing the way we solve problems, let's start by comparing them to the computers we use every day. Traditional computers. Imagine you're sitting at your computer trying to solve a simple problem. You want to add two numbers, say 5 and 3. On a traditional computer, this is a straightforward task. The computer processes these numbers using bits, tiny switches that can be either 0 or 1, performs the addition, and gives you the result, 8. It's a linear process, one step at a time. Easy, right? Now let's scale it up a bit. Instead of adding two numbers, suppose you're tasked with optimizing delivery routes for a large city. You need to consider dozens of factors, traffic patterns, delivery times, fuel costs, and find the most efficient route. A traditional computer would handle this by evaluating each possible route one at a time, calculating the total cost for each. As the number of variables increases, the time it takes to evaluate all possibilities starts to add up. It might take hours, days, or even longer to find the best route. But it's still manageable. But now let's turn the dial even further. Imagine you're a scientist working on drug discovery, trying to find a new medication to fight a deadly disease. Here the problem becomes exponentially more complex. Instead of just a few variables, you're dealing with millions. Chemical bonds, spatial orientations, interaction potentials, and more. Each molecule could have millions of features, and there are billions of possible molecules to evaluate. At this point, a traditional computer starts to struggle. It would have to simulate each molecular configuration one by one, which could take centuries. The problem has grown so large, so complex, that it's practically impossible to solve with conventional methods. This is where quantum computing comes in. Let's turn the dial all the way up. Quantum computers don't just evaluate one possibility at a time. They can explore countless possibilities simultaneously. Imagine being able to simulate every potential drug molecule at once, rather than one by one. What would take traditional computers years, or even longer, quantum computers could do in minutes. This is the true power of quantum computing, solving problems that are far beyond the reach of our current technology. So, whether it's adding two numbers, optimizing delivery routes, or discovering new drugs, quantum computing scales up to handle challenges that traditional computers can't even begin to tackle. It's like turning the dial from 1 to 11, opening up new possibilities that were once thought to be impossible. So, we've seen how quantum computers can handle problems that traditional computers can't. But how exactly do they do it? The magic lies in two fascinating concepts: superposition and quantum entanglement. First, let's talk about superposition. Imagine a traditional computer bit as a light switch. It's either off, 0, or on, 1. But quantum computers use qubits, which are like a magical light switch that can be both off and on at the same time. This is what we call superposition. It means that a qubit can exist in multiple states simultaneously. So, while a traditional computer might be stuck flipping through possibilities one by one, a quantum computer can explore all those possibilities at once, vastly speeding up the process. Now let's add a bit more magic with quantum entanglement. Imagine you have two qubits, like two magical light switches. Normally, what you do to one switch wouldn't affect the other. But when qubits are entangled, something extraordinary happens. Changing the state of one qubit instantly affects the other, no matter how far apart they are. It's as if the two light switches are mysteriously linked, always mirroring each other. This entanglement allows quantum computers to handle complex calculations with a level of coordination that traditional computers simply can't achieve. It's like having a team of synchronized swimmers. Each qubit is working in perfect harmony with the others, solving parts of a problem together all at once. So, superposition gives quantum computers the ability to explore multiple solutions simultaneously, and entanglement allows them to coordinate these solutions in ways that would be impossible for traditional computers. Together, these concepts form the backbone of quantum computing's incredible power. So, quantum computing sounds like it's straight out of a sci-fi movie, right? The ability to solve problems at unimaginable speeds, exploring countless possibilities all at once, is something that could revolutionize everything from medicine to logistics to artificial intelligence. But here's the catch. While the potential is enormous, we're not quite there yet. There are some significant challenges we need to overcome to truly make quantum computing a reality. One of the biggest hurdles is the fragility of qubits. Unlike the sturdy bits in traditional computers, qubits are extremely sensitive to their environment. Even the slightest disturbance, like a tiny fluctuation in temperature or a stray electromagnetic wave, can cause them to lose their state, a problem known as decoherence. This makes it incredibly difficult to maintain the delicate balance needed for quantum computations to run smoothly. Because qubits are so fragile, quantum computers are prone to errors. Traditional computers have error correction built in, but for quantum computers, it's much more complex. Scientists are working on quantum error correction methods, which involve using additional qubits to detect and correct errors without disturbing the original computation. But developing these methods is challenging and requires a lot more qubits than we currently have. Another challenge is scalability. While we've seen some small-scale quantum computers in action, scaling them up to handle millions or even billions of qubits is a massive engineering challenge. We need quantum computers to be stable and scalable to tackle the kinds of problems we've discussed. Building such machines requires advances in both hardware and software, as well as new materials and manufacturing techniques. Despite these challenges, progress in quantum computing is being made at an exciting pace. Major companies like IBM, Google, and Microsoft, as well as numerous startups and research institutions, are pushing the boundaries of what's possible. We're seeing the development of more stable qubits, better quantum algorithms, and even the early stages of quantum networks, which could connect quantum computers together to increase their power. So, when might we see quantum computers truly come to life? Experts are cautiously optimistic. While we might not have fully operational quantum computers handling large-scale, real-world problems by 2030, we could see significant breakthroughs by then. Some predictions suggest that by 2030, we could have quantum computers with enough qubits and stability to start solving specialized problems that are currently out of reach for traditional computers. That said, a lot depends on overcoming the challenges we've talked about. The road to practical, everyday quantum computing is long and filled with obstacles, but the destination, if we can reach it, promises to be nothing short of revolutionary. In the meantime, quantum computing will likely continue to advance in the background, with incremental improvements bringing us closer to a future where these incredible machines are as common as the smartphones in our pockets. Whether it's by 2030 or a bit later, one thing is clear: the quantum revolution is coming, and it has the potential to change our world in ways we're only beginning to imagine. In our next discussion, we'll dive into the fascinating world of robotics, exploring how close we are to building the kind of advanced, rideable robots that can take on incredible challenges. Is it pure fiction? Or could we actually see these mechanical marvels in our lifetime? Stay tuned, because the future of robotics might be closer than you think.